So welcome back to the ultrasound physics and instrumentation. So I will discuss about Doppler principles and instrumentation. You know that in grayscale imaging, the returning echoes have two types of information, and these are echo amplitude and go return time. And according to these two information, go return time and amplitude, the tissues are given two characteristics, mean its distance from the transducer and its brightness. Any reflector reflecting echoes back towards the transducer having high acoustic impedance mismatch, the resultant echo will have high amplitude and that will appear brighter on the display, and vice versa. And similarly, the go return time represents the location of the reflector. If any echo take longer go return time, they will be placed uh, far, far apart from the transducer, and any structure uh, taking less go return time that will be displayed near to the transducer. So these are two important information in the grayscale imaging, but now we are dealing with Doppler imaging. And in cases of Doppler imaging, we have a third type of information, that is shift in frequency or change in frequency. In cases of stationary object, there will be no moment, there will be no change between the reflected and transmitted frequency. For example, if we select a transducer frequency of 4 megahertz, then the reflected frequency will also be around 4 megahertz. There will be no change because with the propagation of sound wave, frequency will never be changed unless there is any moment of the reflector. So the same frequency will be returning back towards the transducer if the reflectors are not moving. But in cases of moving reflector, there will be change in the there will be difference in the receiving and transmitted frequency. The Doppler effect was first discovered by a Christian scientist in 1800 century by Christopher John Doppler. And here you can see that is the Doppler effect. Here again you can see some if the source of sound is moving in any direction, just for example it's moving in this direction, so here you can see the frequency is increasing at the direction where the structure or the source is moving. If the source of the sound is moving towards the receiver, the received waves will have a higher frequency and the shorter wavelength. Just for example, in this image, here, this is the receiver and this is the source, and now the source is moving towards the receiver. That's why the frequency become increased. And here in this image, you can see this is the receiver and this is the source. and the source is moving away from the receiver. That's why the reflected frequency of sound wave having higher, a larger wavelength uh, and lower frequency. So due to the movement of either the receiver or the source, there will be change in frequency. The classic example of Doppler effect is that of a train approaching to a station while sounding its horn. As the train approaches the station, the sound waves from the horn are compressed, resulting in a higher frequency being uh, heard by an observer standing on the platform. As the train moves away from the station, the sound waves are spread out and the observer hears a low frequency sound. An ultrasound, the moving source in the body is blood. Uh, and the receiver is the transducer. Initially, the transducer is the source, and whenever the sound waves are reflected from the blood, then the blood becomes the source, and now the transducer is the receiver. So echo from the stationary reflector in the body tissue have the same frequency and wavelength, and as the transmitted ultrasound frequency A in the following. And each echo from a blood moving towards the transducer have a higher frequency and shorter wavelength than the transmitter ultrasound frequency, and the diagram B. So I'll show you it soon. Here you can see. And the first image, the source is neither moving away nor towards the transducer, meaning it's stationary. So the transmitter and the receiving frequencies are the same. There is no difference between the two frequencies. And the second example, you can see the reflector is moving towards the transducer. So if the transmitted frequency is like this, then the receiving frequency is like this. Because in the first example, the frequency is not affected, and the receiving frequency is like the transmitted frequency. That's why I told you that if the transmitted frequency is like this and the receiving frequency is like this, you can see that the receiving frequency is greater than the transmitted frequency, and that's why the reflector is moving towards the transducer. And the third example, you can see the reflector is moving away the transducer, so the reflected frequency is like this, and the transmitted frequency will be, for example, like this. So there is a difference between these two frequencies, and the receiving frequency is lower than the transmitted frequency, and in that case you can say that the reflector is moving away the transducer. So here you know the important concept that if the blood is moving away the transducer, then the frequency reflected from that blood will be lesser than the transmitted frequency. And in other words, if the reflector or blood is moving towards the transducer, then the reflected frequency will be greater than the transmitted frequency. So this difference in the transmitted and receiving frequency is called frequency shift or Doppler shift. So it is interesting to note that the Doppler effect is a wave phenomena and is not limited just to sound wave. The Doppler effect will occur with any wave. With any wave interaction in which there is relative motion between the source and the receiver. Light wave can also produce the Doppler effect. However, because light travels so quickly, the Doppler effect only becomes perceptible if the motion of the light source is extremely fast. The Doppler shift frequency will now be mathematically represented as Ft is equal to Fr minus Ft. So here by Fr we mean that that is the receiving frequency and Ft is the transmitted frequency. So here the difference is represented by a Doppler frequency or Doppler shift frequency. So FD is the Doppler shift frequency, if R is the received frequency, and FT is the transmitted frequency. If the received frequency is higher than the transmitted frequency, mean if R is greater than Ft, the Doppler shift frequency will be positive. Here you can see if Fr is 4 and Ft is 3, then Fd will be 1 and that will be positive 1. But if Fr is 3 and Ft is 4, then we will have Fd as 1, but that 1 will be negative. So if Fr is greater than Ft, then we'll have a positive Doppler shift. So Doppler shift frequency is negative if the Fr or receiving frequency is lesser than the transmitted frequency. If the received frequency is the same as the transmitted frequency, then the Doppler shift will be 0, mean the structure or the reflector will be stationary. So try it. Pretend you are a Doppler device and see what you can determine. You send out a pulse with a frequency of 3 megahertz and you received an echo back from a moving blood with a frequency of 3.5 megahertz. It's a positive Doppler shift or negative Doppler shift. So you can see the receiving frequency is greater than the transmitted frequency. That's why that will be a positive Doppler shift. Okay. And now try this one. You just, for example, you transmit a pulse with a frequency of 4 megahertz and receiving an echo with a frequency of 3.5 megahertz. So the receiving frequency is lesser than the transmitted frequency. That's why the Doppler shift will be negative and the structure will move away from the transducer, or the structure will move away from you. So if any structure is moving away from the transducer, then the receiving frequency will be lesser than the transmitted frequency. And if any structure is moving towards the transducer, then the receiving frequency will be greater than the transmitted frequency. Is it clear now?
Yes, sir.
In clinical ultrasound, the Doppler shift frequency from moving blood is in the low kilohertz range. We are talking about the Doppler shift frequency. So a typical Doppler shift frequency from normal arterial blood flow moving directly towards the transducer might only be 3 kilohertz. This is a small but definitely detectable Doppler shift frequency. Most normal blood flow will return shift in the 1 to 4 kilohertz range. Abnormally fast moving blood, such is found in a severe stenosis, will return somewhat higher shift in 8 to 20 kilohertz. But again, all the Doppler shift fall in the audible range. It is also important to note that these Doppler shift frequency from both normal and abnormal blood flow fall within the audible sound spectrum, 20 hertz to 20 kilohertz, so that will be heard by human. This means that we can hear the Doppler, these shifts. We can't hear the ultrasound pulse, but we can hear the Doppler shift. But if there is a Doppler shift frequency, we can hear it. If this reason, both pulse Doppler and continuous or Doppler system have loudspeaker which enable the sonographer to listen to the Doppler shift frequencies. These strange noise you hear from Doppler system are exactly that. You are listening to the Doppler shift frequencies. Uh, in most systems, the positive Doppler shift frequency are played by one speaker, while the negative Doppler shift is played by another speaker. So you can see most of the machine are provided with the right and left speakers, and both of them represent the positive. Each of them represent the positive and negative Doppler shift. A positive shift is not a higher magnitude shift, and negative shift is not a lesser magnitude shift, because the sign doesn't affect the magnitude of the shift, but only direction. Because by positive shift, we mean the movement of the reflector is towards the transducer, and by negative shift, we mean that the movement of the structure is away the transducer. So here in this example, if any Doppler shift is minus 5 kilohertz, uh, so that will be the same as plus 5 kilohertz, but the only difference will be that minus shift mean the moment of the reflector is away, and positive shift mean the moment of the structure is towards the transducer. One final important point, the Doppler shift frequency is often simply called as Doppler shift or even shift. That's okay. Just don't forget that it is frequency and in the unit of kilohertz. So what's moving reflector in the body? So you know about the moving reflector in the body, that
RBC.
RBCs are the moving reflector in the body, because that is RBCs that can scatter sound waves. The other moving reflector in the body, just for example, WBCs and platelets, they are not able to reflect the sound wave back towards the transducer. So that's why we will talk about the RBCs, that these are the RBCs which can scatter sound wave back towards the transducer with frequency different from the transmitted frequency. Apart from that, some other fluids are also be detected with the help of Doppler, just for example, urine jet and the urinary bladder and so on. But most commonly, RBCs could be detected, blood could be detected with the help of Doppler. Uh, Doppler frequency, so the echoes from blood are very weak, backscattered echoes, This is why blood usually appear black on the grayscale ultrasound. Because the echoes from blood are so weak, they are easily attenuated by the intervening tissues. In order to ensure that the echoes have enough energy to return to the transducer, Doppler system transmit a lower frequency than the grayscale imaging frequency. For example, if the appropriate imaging frequency or grayscale frequency is 5 megahertz and Doppler mode, if you turn on the Doppler, then the frequency will be uh, changed to 4 megahertz, or you can say that the frequency will be reduced to 4 megahertz because 4 megahertz is selected instead of 5 megahertz frequency for Doppler to be scattered easily from RBCs. This is usually done automatically, but if needed, the sonographer can also change. Sonographic have also control over that knob to change the frequency, the Doppler frequency. I mean, uh, here you can see the frequency is written over here, and this image of 5 megahertz frequency is used for the grayscale imaging. But whenever you are using uh, Doppler over here, so 2.5 megahertz frequency is used. So for Doppler, the frequency is reduced. For exam purpose, you should know that when doing Doppler, the system will transmit at a lower frequency than the grayscale imaging frequency. Uh, Here we'll use the Doppler equation like this: Ft is equal to 2ft cos theta divided by c. Here in this equation, you can see Ft is the Doppler shift, 2 is the coefficient in the equation, which is constant, a numerical value, and you know 2. By 2, we mean though. Ft is the transmitted frequency, and 2 will always be 2, it will never be 3. Ft, that's why we can say that this is constant. And Ft is the transmitted frequency, or you can say the Doppler frequency or the transducer frequency, and we are keeping it constant. Just for example, we have selected a 3 megahertz transmitted frequency, then we'll use that 3 megahertz frequency. Will not change it again and again during the examination. And then we represent the velocity of the moving reflector, and cos theta is the cosine of the angle between the incident sound wave and the moment of the reflector. Okay, so and see is the speed of sound in the medium. Here you can see, so all of these things are almost constant. 2 is constant, ft is the transmitted frequency, that is constant. Just for example, we selected a 4 megahertz frequency, and that will remain constant. Then cosine of the theta, just for example, we have achieved an angle. This is Doppler line, and this is the angle, and that angle is, just for example, 45 degree. Then we will try our best to keep it as 45 degree, to not change again and again, to not to change the value of the Doppler shift. And C, is constant in the soft tissue, and that is 1540 meter per second, and different for different tissues. So that is also constant. And kept as calibration speed by the ultrasound machine as well. So all the variable are constant over here, except v is the velocity of the moving reflector. So here you can say that the Doppler shift is directly dependent upon the velocity of the moving reflector, or you can say the blood. If the velocity of the blood is higher, then the Doppler shift will also be greater. You can say that Doppler shift is directly related to the velocity of the blood. So this is an important information, and with the help of that Doppler shift you can predict the velocity of the blood. So Doppler equation is an important equation for anyone doing Doppler. It is important because it clearly identify all the factors that affect the magnitude of the Doppler shift. Understanding the Doppler equation will enable you to quickly identify the factors that affect the Doppler shift in any scenario. Doppler shift frequency will be positive if the blood is moving towards the transducer, and will be negative if the moving reflector is moving away the transducer. All the factor on the right side of the equation affect the magnitude of the Doppler shift frequency. There are 5 of them. Let's take a look. So we have already taken a look over that, so we no need to look on that. So the Doppler angle is the angle between the transducer and the moving blood. It's important to note that unlike the angle of incidence and in the first module or in the basic ultrasound we have already discussed, the Doppler angle is not measured from the normal. So the Doppler angle will be measured and the angle in between the moving reflector and the incident sound wave. So Doppler angle is the angle between the beam and the blood flow as shown in the diagram. I will show if there is any diagram which will represent the how. Okay, here you can see this is the direction. Just for example, this is the vessel, this is the vessel wall, these are the vessel wall, and the blood is moving and the lumen of the vessel in this direction. So this is the direction of the blood flow, and this is the incident sound wave, and this is the angle in between the flow and the incident sound wave. So this angle will be calculated, and this is actually the cosine. When you will take the cosine of this angle, okay, into account. So here you know that the cosine of the angle 0 is 1, and as we are increasing the angle, the cosine of the angle become decreases, and finally at 90-degree cosine angle, the cosine will become 0. So this is the cosine of the angle, and this is actually the angle. So at 40-degree cosine angle, the value will be 0.77, and at 60-degree angle, the cosine value will be 0.50, and at 80-degree angle, the cosine value of that angle will be 0.17. So as we are increasing the angle, the value of the cosine will become decreased. So you can say that there is an inverse relation between the angle and the value of its cosine. So here in this case, if we are increasing the angle between the incident sound wave and the direction of the movement of the blood, then we will get lower Doppler shift and vice versa.
सर ज्यादातर एंगल्स को 60 से कम रखते हैं ना?
जी 60 से कम रखते हैं।
डॉपलर में ये मैं पैरेलल इसके होना चाहिए साउंड वेव को, या एंगल में होना चाहिए 45 या 60 में?
आपकी आवाज में डिस्टॉर्शन ज्यादा और मतलब नॉइस ज्यादा है और सिग्नल कम है। जरा अपने सिग्नल टू नॉइस रेशो को जरा ठीक करके दोबारा बोले।
सर डॉपलर में जो एंगल है तो हमने तो ये पढ़ा था कि इसको पैरेलल होना चाहिए साउंड वेव को, तो जब एंगल 60 या 40 वो तो ऑब्लिक नहीं हो जाएगा?
अगर किसी और को ये बात समझ आ गई हो तो मुझे जरा बता दे। शोर बहुत ज्यादा है आवाज में। मेरी भी आवाज अगर आप लोगों को इस तरह आ रही है तो फिर तो कुछ भी समझ नहीं आया होगा आप लोगों को।
आपकी
सर
तो
वो यही
क्लियर है
कहना
सर।
चाह रहा है कि पैरेलल बिल्कुल अगर हो जाए इंसिडेंस हम साउंड वेव्स वो पैरेलल हो उसके
हाँ, 0 डिग्री
रिफ्लेक्टेड।
ह्यूमन।
हो, मीन
हाँ
की
बिल्कुल
0 डिग्री हो।
0 डिग्री नहीं, 0 डिग्री तो मैक्सिमम होगा वहाँ पे, तो डेफिनेट शिफ्ट मैक्सिमम प्रोड्यूस नहीं होगी, कॉस 0 1 नहीं है।
नहीं,
सर
आपकी
वो
जो
कह रहे
आप
थे कि ना हम
हाँ,
जितना पैरेलल होते हैं उतनी ज्यादा मैक्सिमम शिफ्ट मिलती है, लेकिन 60 45 30 एंगल पैरेलल तो नहीं है।
नहीं तो
यस।
देखिए, इस तरह मतलब 0 डिग्री एंगल तो अचीवेबल नहीं है ना। मीन कि बहुत कम वेसल में आप 0 डिग्री एंगल को अचीव कर सकते हैं। तो इसका मतलब ये हुआ कि 60 डिग्री से कम कोशिश करें।
कम
तो कम से कम
जी
जितनी भी हो तो इतनी बेहतर है। अब अगर आप 0 डिग्री को अचीव कर सकते हैं, दैट विल बी बेटर। लेकिन 0 डिग्री अचीवेबल बहुत कम रीजन्स पे है। जस्ट लाइक आप किडनी का अल्ट्रासाउंड कर रहे हो और मतलब जो किडनी में वेसल जो है मतलब वो टुवर्ड्स द कॉर्टेक्स जा रही है, तो वो आपके टुवर्ड्स द ट्रांसड्यूसर आ सकते हैं, 0 डिग्री एंगल अचीव हो सकती है। लेकिन अगर आप किसी के जो है मतलब ब्रेकियल आर्टरी देख रहे हो, तो ब्रेकियल आर्टरी के साथ 0 डिग्री एंगल कैसे आप अचीव कर सकते हैं?
नहीं हो सकता, मुश्किल है सर।
हाँ, तो फिर इसके लिए ये होगा कि बेटर डॉपलर शिफ्ट के लिए कम से कम एंगल, जितना कम एंगल हो सकता है इतना आपको
हाँ
डॉपलर शिफ्ट अच्छा मिलेगा।
मुझे इसे कर दो।
ठीक।
यस।
अच्छा, ये अभी जैसे कि आपके सामने है कि कोसाइन ऑफ 0 डिग्री इज 1, कोसाइन ऑफ 60 डिग्री इज 0.5 एंड कोसाइन ऑफ 90 डिग्री इज 0। तो जितना आप मतलब कि एंगल बढ़ा रहे हो इतना इसका कोसाइन कम हो रहा है। एंड एट 90 डिग्री एंगल देयर विल बी नो डॉपलर शिफ्ट एट ऑल, क्योंकि आपने उसी इक्वेशन में एक भी 0 लगा दिया तो सारा डॉपलर शिफ्ट ही 0 हो गया। तो अगर 90 डिग्री एंगल हो, जस्ट फॉर एग्जांपल ये वेसल है और यहाँ पे आपका ट्रांसड्यूसर पड़ा हुआ है एंड देयर इज a right angle between the incident sound wave and the movement of blood। अब ब्लड देखिए, चाहे इस डायरेक्शन में मूव कर रहा है या इस डायरेक्शन में मूव कर रहा है, लेकिन यहाँ पे इंसिडेंट साउंड वेव के साथ इनका एंगल क्या बन
90
रहा है?
डिग्री
90 डिग्री।
90
और जब 90 डिग्री हो गया तो इसके लिए कोसाइन 90
0
डिग्री के जो है 0 है और डॉपलर
डॉपलर
शिफ्ट
शिफ्ट
क्या
0
हो जाएगा? 0 हो जाएगा, क्योंकि हमें
0
पता है कि
0
एफ डी इज इक्वल टू 2
2 FTB
एफ
cos
टी
theta
वी कॉस थीटा
over C।
डिवाइडेड बाय सी। तो इसमें ये आपने 0 कर दिया इनकी सारे की जगह, तो ये बाकी सारे इसने 0 कर दिए और आपके पास डॉपलर शिफ्ट 0 हो जाएगा। तो इस किस्म की वेसल में आपको किस किस्म का ब्लड फ्लो नहीं मिलेगा। अगर चाहे इसमें 400 सेंटीमीटर पर सेकंड की वेलोसिटी से ब्लड फ्लो क्यों ना कर रहा हो, तब भी इसमें आपको किसी न कलर डॉपलर पे कलर मिलेगा, न स्पेक्ट्रल डॉपलर पे इसका स्पेक्ट्रम मिलेगा, क्योंकि इसमें वेलोसिटी डॉपलर जो एंगल है वो 0 है। Is it clear?
यस।
यस सर।
मैं समझ रहा हूँ कि मतलब डॉपलर तो बेसिक्स जितनी भी है आप लोगों को समझ आ गई। ये जरा
अच्छा।
इस पे जरा गौर कर ले, अब इससे आपको और भी क्लियर हो जाएगा। With the reference of this adjacent diagram, which situation would produce the greatest Doppler shift? जल्दी बताए, जल्दी बताए।
सर ये जो डायरेक्शन बताई हुई है ये ब्लड की है?
हाँ जी, ये जो
से जो
डायरेक्शन
मूव
है
कर रहे हैं
ब्लड की है, बिल्कुल ब्लड की।
और ऊपर से ट्रांसड्यूसर बिल्कुल वो स्ट्रेट है
हाँ बिल्कुल
उसकी
है
इंसिडेंट पे।
जी। क्या कर रहे हो अल्लाह के बंदे, जल्दी बता दे। चले हम मतलब ऐसे मतलब इसको डिस्क्राइब करते हैं। ए नंबर में कोई डॉपलर शिफ्ट होगा?
नहीं
नहीं होगा, क्योंकि एंगल
जीरो
जो है वो क्या है, वो 90
90
डिग्री।
डिग्री।
इसमें डॉपलर शिफ्ट नहीं होगा, तो ये तो बीच में से निकाल दे। अब इसी तरीके से इसमें डॉपलर शिफ्ट होगा? नहीं होगा,
नो
ये इसको भी निकाल दे। लो
परपेंडिकुलर।
जी, दो तो गए, अब तीन ऑप्शन रह गई। अब जब आपके पास तीन ऑप्शन रह गए, तो ये बिल्कुल डायरेक्ट टूवर्ड्स है, ये डायरेक्ट अवे है, तो इन ही दोनों के दरमियान कंपटीशन है, ये तो बीच में से निकाल दे, क्योंकि ये तो ऑब्लिक है। ठीक हो गया ना? तो हाईएस्ट डॉपलर शिफ्ट हमें या तो बी में मिलेगा या ई में मिलेगा। अब अगर आप देखें तो बी में वेलोसिटी जो है वो 100 सेंटीमीटर पर सेकंड है, और ई में वेलोसिटी 50 सेंटीमीटर पर सेकंड है, और फ्रीक्वेंसी दोनों में 5 मेगाहर्ट्ज यूज हो गई है, तो किसको डॉपलर शिफ्ट ज्यादा होगा? ये तो अभी बात हो गई थी कि डॉपलर शिफ्ट इज टोटली रिलेटेड टू विद वेलोसिटी ऑफ द ब्लड। तो जितनी
जी सर,
वेलोसिटी
जी
ज्यादा
सर।
होगी, इतना जो है डॉपलर शिफ्ट ज्यादा होगा, तो
बी।
बी इसका
और बी में
करेक्ट।
होगा।
If
ठीक
the
हो गया
vessel
ना?
is moving away from the transducer, negative Doppler shift B sir.
हाँ जी। अच्छा, डॉपलर इंस्ट्रूमेंटेशन इंशाल्लाह हम नेक्स्ट क्लास में पढ़ेंगे, ठीक है? तो उस वक्त तक के लिए जो है मतलब ये पूरा याद कर ले, पक्का कर दे। नेक्स्ट क्लास में मैं
ओके सर।
इसका जो है साथ साथ में आप लोगों से इसके बारे में पूछूंगा भी। और मैं समझता हूँ कि इसमें अगर